Hello everyone, my name is Kadir. This is our assignment 2. So, in this video, I will walk you through my implementation of multi-class classification using the iris dataset. I will explain the code step by step and answer key questions related to the model performance, overfitting, and optimization techniques. Let's get started. So, I will just do the first one. So in the first step, we mount Google Drive so that we can access the iris CSV file stored in our collab folder. I run this and I import the necessary libraries. So to read the file, I need to use my file path, which is here, and read the CSV file and display the first few rows to verify the hat. So this shows the first 5 rows on the dataset, including the sample length, sample width, paddle length, paddle width, and species. And as you see here, it's also the same in the first 5. So the next one, convert the last column to integers. This species column contains the string values. Since machine learning models work with numbers, we convert these categories to numerical labels. This maps Setosa to 0, Versicolor to 1, and Virginica to 2, making it suitable for the classification. So it's also same on here. I'll just run these codes again. So splitting features and labels, we now separate the dataset into features X and labels Y. The first 4 columns are input features and the last column is the target label. So this is for X, this is for Y. This means X contains numerical values for classification, while Y holds the categorical labels. And I'll run these two. Now it's time to split data into training and testing sets. So we use 80% of train and 20% of test to evaluate the model performance. There's a random state here and there's a random state here. The random state ensures reproducibility to so that we all get the same split. And check the first 5 rows. Here we go. So I'll jump into the 5A. So converting labels to one hot encoding. So here, since this is a multi-class classification problem, we apply one hot encoding to transform the categorical labels into numerical vectors. This converts each label into 3-element vector, making it suitable for neural networks. So defining the neural network model here. Now we define the sequential neural network with 3 layers. The first 2 layers have 100 neurons and use ReLU activation, which helps in the learning complex patterns. The final layer has 3 neurons with softmax activation, so converting outputs into probabilities for each classes. So this is the softmax, this is the ReLU, they were first 2. And then now next we compile the model using the RMS prop, optimizer, and categorical cross entropy loss. For the 7, train your model using epoch 20, batch 10. We train a model using 20 epochs and the batch size of 10. Each epoch means the model goes through the entire dataset once. For the batch size of 10 means updates happen every 10 samples, as you see here. And then after training, we evaluate the model on the test dataset, calculate the results, and test accuracy. Test accuracy is like 96.67. Rebuilding the model with different parameters. In the first, second hidden layers, 10 hidden units, and so we use different parameters here. And then we change the 5 different aspects one at a time. There, like reducing the number of layers. This is a different thing. So we change some of the specific things. We reduce the layers and calculate again. So for the like number 10, for the video submission, like it's ensure how the number of layers hidden. So it's basically like if I go to the like first one, or any hidden units could impact accuracy of our model. Yeah. So like the number of layers and hidden units, like at the same time, it's neurons in the neural network are like important factors that influence the model's capacity to learn pattern in the data. So more layers, more neurons. Adding the layers increases the complexity of the model, allowing it to learn more like patterns. However, this could also lead to overfitting, especially if the model becomes too complex for the dataset size. So do we always suffer from overfitting? No, we don't always suffer from overfitting. It depends on the size of datasets, the complexity of the model, the regularization techniques. So how can we detect overfitting? It's like there's some methods to detect. It's like monitor training, vs like validation loss. Overfitting is like typically detected when the model performs well on the training data but poorly on the validation or test data. So if the training loss continues to decrease but the validation loss starts to increase, this is a strong indicator of overfitting. Training accuracy improving but validation accuracy stagnating or decreasing suggests overfitting as well. So cross-validation, this technique involves splitting the dataset into multiple subsets and training multiple models. If the model performs well on all subsets, it's likely to be overfitting. And the last question, how can we reduce overfitting? So early stopping, like stop training when the validation loss stops improving. This prevents the model from learning too much noise in the data. Regularization, techniques like L2 regularization, weight delay add a penalty to large weights, forcing to the model to generalize better. Dropout, data augmentation, simplify the model. So yeah, that's it. Thank you for watching. Have a good day.